Another exit at the back, so you can also accumulate there if you want to. I have 2 more hours to tell you about stuff. Essentially what I plan to do is spend the bulk of those 2 hours using the electronic board, but at the end I will actually use some slides to show you some more currently ongoing research based on the Lieb-Liniger model. Last time we left it at this, the Yang-Yang thermodynamics of the Lieb-Liniger model, this kind of unified formalism where we get a single integral equation that we need to solve, giving us all the equilibrium properties. Essentially this epsilon of k describes a saddle point state of the Gibbs distribution, and this saddle point state is an eigenstate that essentially is characteristic of all the equilibrium properties of this system. Were there questions about what we did last time? Okay, because now I'm not going to talk about thermodynamics anymore. What I plan to do today is go back to excitations, just polish up a little bit our type 1 and type 2 modes. And then I want to talk about some crazy thing, the attractive Bose gas, tell you a little bit about that, and then we move on to other things. So are there questions about last time, or is everything crystal clear, or just too boring to ask? Okay, well, let's carry on. Okay, so what we're going to do is actually revisit excitations in the light of what we've done with the Yang-Yang formalism. So excitations revisited. Now, I'll change notations a tiny bit because, so in the Lieb-Liniger Bose gas we had these parameters k that were solution to the beta equations that were these quasi-momenta, and the total momentum was just the linear sum of these k's. Now, this is true for the Lieb-Liniger model, but in other models, typically what happens is that you prefer parameterizing your beta equations in terms of other variables that are not directly the momentum. So we call them rapidities. So the notation that I'll be using today is a little bit more that the solutions to the beta equations will be in terms of lambdas, that will be these rapidities. Okay? Many of the equations I'll write today are also more or less directly applicable to other models, so I'll just, use a slightly more uniform notation than we've done in the past. Essentially, what we will do, first of all, is introduce some bare momentum. That's momentum, you can clearly read. And energy functions. Okay, which is k0 of lambda is equal to lambda for the, I'm still falling off the earth right there. Yeah. So for the Bose gas, the bare momentum k0 of lambda is just equal to lambda, and the bare energy E0 of lambda is just lambda squared minus mu. Okay, so then when we look at the zero temperature limit of our Yang-Yang equation, this one here, essentially we observe the following fact. So there's a chemical potential in there that would take to be some positive number if your interactions are very, very small, and otherwise can be of any sign. But the point is that the function epsilon of k for positive mu, you expect it to change sign at some value of k. Right? So if you go to the low temperature limit, so you put t is equal to 0, then of course the integral kernel on the right hand side is such that you only care about it if epsilon is less than 0. If epsilon is greater than 0, the whole thing just collapses to 0, so that doesn't work. So when we take the zero temperature limit of this equation here, what we obtain is an integral equation for the value of epsilon k within the Fermi surface. Okay, so let's just write this down. So t to 0 limit of Yang-Yang essentially just tells us that epsilon of lambda minus the integral from minus lambda f to lambda f, these being the boundaries and rapidities of our Fermi C. And then we had our kernel C lambda minus lambda prime, okay, epsilon of lambda prime. This was then equal to epsilon 0 of lambda. Okay, so this is the integral equation that we need to solve in order to characterize the ground state. It is equivalent to the Lieb equation, if you want. It's just kind of rewriting of it. Now, what we can do is just introduce some notation. You'll see there's a lot of black magic when you do calculations with thermodynamic beta ansatz. Very often you have the feeling that you're kind of taking the Lieb equation, substituting the Lieb equation into the Lieb equation, manipulating it a little bit, and then resubstitute again the Lieb equation in there, and then you get something else. Okay, so it's going to have a little bit that taste, but you'll see it's part of the game. So what we do is that we simplify notations a little bit. We just define the following. So define an object that I will denote. I'll try to be a little bit careful here. I'll denote it as a two-parameter function, c sub f of lambda lambda prime, and this is just our beloved kernel, but with a restriction on the value of the second argument. Okay, so this second argument, lambda prime, is within the Fermi sea. So what we can do is just rewrite this equation here in the following way. We say that it's just 1 minus Cf convolved into epsilon of lambda is equal to epsilon 0 of lambda. Okay? So now the fun fact. So what we do with this is that we want to invert this, this integral operator here. So we'll just introduce some notations for this. So formal inversion. What we will say is that there exists an operator that I'll write as L, which when I convolve it with 1 minus Cf, this gives me 1. Okay? So in terms of functions, you know, when I write 1 here, I mean a delta function, right? So it's just an integral curve. Now, you know, the simple consequences of this, so you have, for example, that just the application of 1 plus L on the CF. So these are just equations that are going to be useful for later. This is just L, and also you just have that L started into 1 minus Cf. Okay, it's very quite simple. This just becomes Cf. Okay, so what we do then is that we use this inverse operator here to write our solution. Magic, you know, we found our solution. Epsilon of lambda is just equal to 1 plus L convolved into epsilon 0. Okay, so we've solved our Einstein equation. Okay, the Lieb equation, if you want, you can also write it. You can formally solve it as rho. Let me now give an index g to specify that it's the ground state, rho here. So rho ground state of lambda is just equal to 1 over 2 pi times the operator 1 plus L convolving, you know, the 1 here. You know, kind of 1 of lambda if you have used the notation. And here, so the lambda is within the C, right? Okay, so these are just formal ways of writing our solutions. Okay, now what I want to do is go back to the equations that we had for the excitations. Because what this will lead to is a nice interpretation of this function epsilon of lambda. Okay, so let's just do that. We had an equation for the displacement. So displacement of type 1 modes. Okay, and this was equation 1.99, if you have the notes from last time. 1.97. Do you have the notes from last time? Okay, so this equation for the displacement, you remember what that was, right? So you had a type 1 excitation, you give it a certain rapidity, and then all of the other rapidities, because of the beta equations, move around a little bit. This displacement characterizes this movement of the rapidities, which is an order 1 over L effect. So the equation for the displacement you can just rewrite in the following way. So you just have 1 minus CF. We had an integral equation for this displacement. Start into the displacement at lambda coming from a particle at lambda p. Just kind of using now rapidities for that. So this was equal to minus 1 over 2 pi times pi plus the scattering phase shift that we had of lambda minus lambda p. Okay, so here in this equation you have again that lambda is less than lambda f because otherwise the displacement vanishes. And this lambda p, I'll just put on the right hand side so it's greater than lambda f. Okay, so you can now start playing tricks. So for example, let me show you a little trick. So trick. The right hand side is just the scattering phase shift here. Therefore it is the integral of the derivative of the phase shift. The derivative of the phase shift is just our kernel c. Okay? So what we can write is that the right hand side is equal, it's just a straightforward little calculation. It's 1 over 2 pi integral from lambda p to infinity, okay, d lambda prime of d lambda prime of phi of lambda minus lambda prime. Okay, so it's just simple identity, and this essentially becomes equal. Let me try to write it here. So this just becomes equal to minus integral from lambda p to infinity d lambda prime, our kernel that we have, lambda minus lambda prime. Okay, just a straightforward identity. So what do we do? Well, we have this equation for the displacement here, 1 minus c with the d. In order to invert this integral equation, we apply 1 plus L on this, okay? But 1 plus L acting on C, 1 plus L acting on C is L. Therefore, we get an explicit solution for the displacement, d of lambda p, okay, is simply equal to minus integral lambda p to infinity d lambda prime L of lambda prime. Okay? So we're just kind of writing formal solutions for our functions this way, all relating. Okay, so that's very nice. But now let's use these things to do something a little bit more physical. Now we have the displacement, which is not observable, so let's consider the energy of type 1 excitations. Energy of type 1. Okay, so this was equation 1.99. Okay, which again we can rewrite. So let me just write the energy of a type 1 mode at lambda p as omega 1 of lambda p. Okay. And this thing we just have epsilon 0 of lambda p. So if you have your notes, you'll recognize just a change of notation here. Plus the integral from minus lambda f to lambda f d lambda of now just d epsilon 0 of lambda d lambda times the displacement lambda p. Okay, so this is just textually rewriting the equation that we have in terms of the displacement. The epsilon 0 d lambda is just 2 lambda. It's just 2k in that equation. Okay, so we just manipulate this. So this is epsilon 0 of lambda p. And now that we have our explicit solution here, it becomes minus the integral from lambda p to infinity, d lambda prime, integral minus lambda f to lambda d lambda of our L lambda prime times d epsilon 0 d lambda. Okay, at lambda. Okay, that's fine. Now what we can do is use the following equation. 1 minus the kernel CF starred into d epsilon d lambda is equal to d epsilon 0 of lambda d lambda. Okay? This is a simple consequence of the Yang equation for epsilon by simply taking a derivative with respect to lambda and using the fact that the kernels vanish at infinity. Okay? So you just can, you see, d epsilon d lambda obeys a similar integral equation to epsilon of lambda, just with the different kernel, different driving term on the right-hand side. Okay, so instead of the driving term being lambda squared minus mu, it's now just 2 lambda. Okay? But that doesn't matter. So essentially from this, what we can do, what we can obtain is that L starred into d epsilon 0, that's u, d lambda is equal to CF starred into d epsilon d lambda. Yeah, we can just see this maybe. Okay, so what we have is that the entries where we have epsilon 0 here do occur in the form of a convolution with L, but the convolution of epsilon 0 with L is really something that knows about epsilon. So then we replace this term here by these contributions here. You need to substitute both these equations in there if you want to see it clearly. And then what you get is that the dispersion, so the energy associated to a type 1 at lambda p, is equal to epsilon 0 of lambda p, okay, minus the integral from lambda p to infinity d lambda of now, just using this equation, d epsilon d lambda minus d epsilon 0 d lambda. Okay, so that's kind of magical, because it just becomes epsilon of lambda p. Okay, so using epsilon minus epsilon 0 at lambda goes to infinity is equal to 0. Okay, so epsilon minus epsilon 0 just goes to 0 as lambda goes to infinity, because then the integral, so the epsilon becomes very, very large. The integral kernel has 1 plus e to the minus epsilon over t, so this all goes to 0, so epsilon becomes equal to epsilon 0. Okay, so that's what we have. You see, if, this is kind of a nice equation, right? If you have a type 1 excitation in your system at rapidity lambda p, then the energy it carries is simply epsilon of lambda p. So epsilon is indeed a true physical energy function for the excitations. So it looked like an energy function in the free energy that we wrote a la Yang, but indeed, if you construct these excitations, the type 1 modes, then they have this dispersion relation. Okay, now it's still in terms of the variable lambda p, okay, and lambda p is really the solution to the beta equations, so it's not, it's the rapidity, it's not the momentum. So now we have to calculate the momentum of the excitations. But that's their energy. Okay, so for the momentum, what we have is that the momentum, let me write it like this, the momentum of type 1 modes at lambda p, this was equation 1.98, which you just rewrite in the following way. So this just becomes lambda p plus the integral minus lambda f, so lambda f, the lambda of the displacement, lambda p. Okay, so essentially, let me just refer to the notes, which you don't have yet, right? So maybe I can just kind of go very quickly through this. So CF notes. Okay, so using very similar manipulations here, we can just rewrite this in terms of our kernel L. Okay, some integral of our kernel L, and then just do manipulations to obtain a, well, I don't know. I don't feel like doing it. Do you feel like me doing it? Or do you trust me that it's in the notes? Because otherwise I don't have time for other stuff, so I'd rather tell you other stuff. Just follow the notes, the same logic. Essentially, what you obtain is that the momentum of these excitations, lambda p, is equal to some formula which is not quite as nice as this one here, but still you have the integral from minus lambda f to lambda f d lambda. And now what appears is the scattering phase shift, lambda p minus lambda, times the density function in the ground state, rho g of lambda. Okay, and then there's just a little correction plus pi times n. Okay, and here in this equation, lambda p is greater than lambda f. Okay, so just a few steps here, but of very similar nature. It's just a question of inverting the integral kernels, and you get this. Okay, now we have the energy, we have the momentum as a function of lambda. So what we can calculate essentially is the group velocity of these excitations. Okay, so d omega dk, or d omega dp. So let's just do that quickly. So the group velocity of type 1. So we'll just have v that we'll write as vf. And this is going to be d omega 1 dp1. And this we can just write as, just using the chain rule. So this is going to be the d of the, well, I'm now introducing notations here. It's going to be d of the epsilon of the ground state, okay, with respect to lambda at lambda f, divided by, maybe I'll just move this a little bit. F got lost. Okay, at lambda f, divided by just the change of momentum with lambda at lambda f. Okay, so essentially what we have is that from the equation for the momentum, let's just calculate the denominator here. So dp d lambda at lambda f, just straight from the equation that we had on the previous page. This is just lambda f, sorry, just 1, plus 2 pi integral minus lambda f to lambda f d lambda. And now when I take the derivative, I let the derivative act on the phi, so the phi becomes the c times rho of where this is the rho ground state. Okay? And using the Lieb equation, this is just equal to 2 pi rho ground state at lambda f. Okay? So what we have is that this velocity is equal to the epsilon ground state of lambda d lambda evaluated at lambda f divided by 2 pi times the density of roots at lambda f. Okay, so that's an expression, an explicit expression for it, because now we have our thermodynamic equations. We obtain an equation for the epsilon. We plot this function. We obtain also, in the same time, the density, rho g. And now I ask you, okay, so what is the characteristic velocity of the excitations that I have in here? Well, you can calculate it explicitly for a given value of c and for a given filling by solving these equations. Okay, so you'll see later some data I'll show you that kind of sees this VF quite clearly. Okay, so that's how you would calculate the velocity in these models. So for example, if you do CFT or if you do Bosnization, things like that, you need a velocity. And this velocity is an input to these theories. So that's how you would use thermodynamic data ansatz to provide this input. Okay? Now, so there are just some little comments that I can do. So type 2. Similar logic. So the energy of a type 2 mode at lambda whole is equal to minus epsilon ground state of lambda whole. Okay? And the momentum P2 of lambda whole is really just minus the momentum of the type 1 nodes if you were to evaluate it at lambda whole. Okay, so you add a hole, you remove a particle, you get this energy and this momentum. Okay? If you have a number of type 1 excitations and a number of type 2 excitations, then the energy that you have is the summation over all these things. So the summation of epsilon of lambda, call it particle I, minus the summation over the whole contributions. Okay, and the same thing with the momentum. Okay, so this might seem like a trivial statement, but actually it's quite remarkable when you think about it. We have a gas at finite density, and what we are doing now is constructing explicitly a new basis for the Hilbert space. Because we have the ground state, which we consider as a vacuum for new forms of excitations. Okay, so instead of having the true vacuum without any particles, and then we apply Psi-Dagger to create things. Yeah. Here, what we do is that we redefine the vacuum as the ground state of the theory. And now there are two types of excitations that we would like to have here. So there's a particle and a hole, independent excitations. And if we construct a finite number of these excitations above the ground state, then the energy is purely additive. That means that these excitations, they do not interact. They are free excitations. Okay? They do not interact with each other. You put 10 type 1 nodes, you add another one, it doesn't matter. There's no mutual interaction between the type 1 nodes in the thermodynamic limit. Okay? So what you have done is that you have found a new free basis for the theory. So we're still an interacting Bose gas, but we have a free theory. It's just a free theory with a strange dispersion relation that you solve that is completely determined by the ground state. So the ground state configuration completely determines not only all the thermodynamic properties, I mean, it's kind of related, but all the spectrum
around the ground state is also determined by simple equations using the ground state distributions. Okay, so if you know the ground state is able to lift itself quite far in the Hilbert space. Okay, so that's how you would kind of understand all these, or maybe all these correlations that I'll show you later around the ground state. You understand them in terms of these excitations here. Okay, so that's just kind of a wrap up of our discussion about the excitations here. Now the excitations, type 1, type 2, they are completely characterized. Our job is finished because we have explicit solutions for everything. Okay? Are there any questions? Yes?
Did we show the existence of L?
I didn't show it, but it does exist. So I'm giving you a kind of a series of notes where you have some of the equations in there, but I'm writing up the notes where it's clear that you see that everything's okay. So there's a discussion about that in Koryepin, there's a little detail that they do in there, which is a bit questionable, but you'll see. One day my book will come out, and then you'll get it. So the nice thing is that this C operator is a very innocuous operator. Okay, so it has good values at infinity, and if you look at the eigenvalues of this operator, you see that they're non-degenerate, that they don't vanish, etc. So then it's invertible. But they're, with the notations, just the symmetry properties of this, you have to, like this L operator, it's not a symmetric function of lambda and lambda prime. But these are just little details. So there's no real worry, no. And in practice, of course, if you do it on the computer, you can do all that.
So if we were to calculate the S matrices of the excitations, taking into account the underlying Fermi seeds, we would find what, 1 or -1. So these are really non-interacting excitations.
Well, in a sense, so you get a non-trivial S matrix for these asymptotic states if you want, right? And then it's so the calculation for that is done in the book, in the Koryepin book.
Yeah, this is the method of Koryepin, right?
Yeah, that's right.
But you don't get a -1. In this sense, they still interact.
Yeah, if you want, but it's kind of a statistical interaction, right? It's not like interacting in the sense that if you were to write an effective theory for the low-lying states in terms of these excitations, that you would need to have two body terms in the operators creating those excitations. This is not the case. Okay? Okay, so that finishes our discussion of the excitations. Now, there's one thing which I want to talk to you a little bit about because it's related to essentially CFT and things like that. So another supplement here concerns finite size corrections. Okay, so essentially what we will consider is just the slight modification or tuning away from the thermodynamic limit and see what effect that has on the theory. So we just had a couple of things. So the energy of a state was just the summation of these bare energies, okay, of the solutions lambda j to the beta equations, and the momentum was similarly just the summation over j of this k0 of lambda j. Okay, so we had the beta equations. Let's write them straight for the ground state. Okay, so let's write them straight like this. K0, and then let me write the ground state rapidities as lambda j0. Okay, this was equal to 2 pi times the quantum numbers of the ground state, and these were as follows. So there were minus n plus 1 over 2 plus j. Okay, so for a generic excited state, we would just have different quantum numbers here. Okay, so the ground state energy is just the following object. So you just have, well, over L, it's 1 over L, the summation of this epsilon 0 of now the function k evaluated at these integers. Okay, you remember when we did the thermodynamic limit, there was this function k of x that we had defined, so this is this function here. Okay, so let me do that very quickly because the calculation is slightly, well, it's relatively straightforward but slightly technical. What you do is that you just, you see, you have an evenly spaced lattice in the space of quantum numbers. Right? But of course, the rapidities themselves are not evenly spaced. So what you do first is that you write this as an integral in quantum number space. You've got the evenly spaced lattice, so what you do is that you just invoke the Euler-Maclaurin summation formula here. Okay? And this will give you corrections to the form. Okay, so you invoke Euler-Maclaurin. Okay, the second form. I've written it in the notes actually, but let me just write the result. I'll just tell you what these things are. dx, and now epsilon 0 of k ground state of x. Yeah. And then there are these little corrections, minus 1 over 24 L squared with the variation of epsilon 0 written x space dx minus xf to xf plus order 1 over L to the 4. Okay? So this xf here is just the limit of quantum numbers that we have for a certain filling, and we define it here as n over 2L. Okay, so this xf here, if you go back to the quantum numbers of the ground state here, so you know that the last quantum number is n minus 1 over 2. Right? So you just kind of go a half step beyond. So the Fermi boundary is just a half step between the occupied quantum number and the next available quantum number. And this means that this coordinate, this quantum number over L, is just defined as this. Okay, so really this is, I mean, you've done Euler-Maclaurin before, right? So when you've evaluated integrals numerically and things like that, so you know you get the summation and then you get these derivatives at the boundaries that you need to take into account. Let's say that. Yeah? Familiar? Okay, that's all it is. Now the thing that we have, of course, is an integral in the space of quantum numbers here. So you remember when we did the first limit to the first move towards the thermodynamic limit, we had these densities in rapidity space. And one of the densities was this total density. And this total density was dx dk. In this language here, dx d lambda. So this is the mapping between quantum number space and rapidity space. So what we will do here is just use this Jacobian to go to the rapidity space. But of course, we're considering the ground state here. And the ground state is characterized by the fact that the density over the interval within the Fermi sea is equal to the total density. Okay? So the rho total is equal to rho when you're within the interval of the ground state. So immediately what you have is that you can rewrite this thing here. So the ground state energy is equal to L times integral from minus lambda f to lambda f d lambda of epsilon 0 of lambda, rho of lambda, rho ground state of lambda. Okay? And then you just need to change these things here. So there's you just use this this relationship that we had dx d lambda. So there's the rho that comes here. So what you get is that it's minus 1 over 12L, and then 1 over rho ground state at lambda f times d epsilon 0 d lambda evaluated at lambda f. Okay? Plus order 1 over L squared. Okay, where lambda f is here by definition the function that we have, this continuous function that we have written, evaluated at xf. Okay, it's again completely explicitly determined. Okay, now I have to be a little bit careful here because when you do this replacement, there can be a correction to order 1 over L of this density function here. So let's just write that down explicitly. Okay, so where rho g L of lambda is the ground state density, correct up to subleading order. In 1 over L. Okay, so it obeys the equation as follows. So rho g L of lambda minus the integral from minus lambda f to lambda f d lambda prime, c of lambda minus lambda prime, rho g L lambda prime, okay, is equal to 1 over 2 pi d k0 d lambda, evaluated at lambda. Okay, so this is just like the equation that we had, it's just like the Lieb equation. But of course, when we rederive the Lieb equation, keeping subleading terms to order subleading in 1 over L terms, we get another contribution that comes similarly from the Euler-Maclaurin summation. So this term changes the driving term here. So on the right-hand side, there's an extra 1 over 24 L squared rho g of lambda f, where this one here you can replace by the thermodynamic one without making an error. And now there's a d lambda of just the boundary contributions here, c of lambda f minus c of lambda minus lambda f. Okay, so it's just an extra correction term that you have. So what we can do is write an expansion. So we can take rho g L of lambda is equal to rho g of lambda, where this is just the one that you compute with the thermodynamic limit, plus 1 over L squared. Let's write it rho g2 of lambda. Okay? We're almost there. Okay, now, once again, there are manipulations that maybe I can just refer to the notes form, because that's it's kind of the way to avoid rewriting this. So doing very similar manipulations to what we did to treat the energy and the momentum of the type 1 excitations, here you can just do integral manipulation. So once again, what I have here is just 1 minus Cf applied onto this rho. Okay, but then I substitute this expansion here and I write an equation for this rho g2. Okay, so there's going to be something like 1 minus CF applied to rho G2 is equal to this kernel here. This kernel is just a derivative of C. When I apply 1 plus L onto this, also I get that things simplify. Okay, and I can just manipulate all these things, and what I obtain, and again, you'll have that explicitly in the notes that will be given to you maybe at the break or something, I don't know. The photocopying machine was busy. So after some steps, you get the following. You get that the energy of the ground state is equal to some extensive part, right, plus then some order 0 in L, plus some 1 over L E1, plus order 1 over L squared. Okay, where EG, the extensive energy density, is just the integral minus lambda f to lambda f d lambda of the epsilon 0 function times rho ground state of lambda. The 0th order, actually here it vanishes. Okay? And the first order in 1 over L, again, is some very nasty combination of functions that suddenly collapses back onto very simple terms. So that's a challenge for you to derive that without looking at the notes first. Essentially what you obtain is that it's minus pi over 6 times the Fermi velocity that we had calculated before. Okay? So you'll see in the notes, it's all like that. So this is a Casimir energy. Okay? And if you know a bit of conformal field theory, you know that the corrections to the ground state energy, the 1 over L corrections to the ground state energy, they're universal. So they tell you something about the central charge of your theory. So here it's a C is equal to 1 theory, and the VF naturally occurs in here because, yeah, it's a dimensional analysis. Okay? So once again, the actual derivation of this is in the notes, and there's no more magic to it than using Euler and Maclaurin, and then once again substitute the Lieb equation into the Lieb equation about 10 times over, and then you get there. Okay, so but if you reproduce these manipulations, you'll know very much how to calculate many things in these models. Okay, so. Now I wanted to switch to the attractive gas, but maybe I should give you a break first. Okay, so yes.
Could you guess it was critical from the start?
I'm sorry.
Could you guess it was critical from the start?
Well, so actually the point at which you can start thinking that you might have the hope of doing some CFT things is when you calculate the excitation energy of the type 1 and type 2, and you notice that there's a linear term. Okay, so we calculated the group velocity, and the group velocity was finite. Well, actually, we didn't show that it was finite, but it turns out that it is finite. So if your C is greater than 0, then there is essentially a linear part to your spectrum, and that's all you need to have CFT in this case. So if you, actually, I mean, if you want here, you can go further. Okay, so we've calculated the Fermi velocity. Of course, the dispersions that come from the solution of the TBA equations, they're not perfect lines. They will have a curvature. You can actually calculate this curvature term. And what's this curvature term? It's like an effective mass for these excitations. Okay, so this goes beyond CFT. But you can calculate the effective mass for these excitations from TBA considerations. Actually, so there's so there's a paper from about 6 years ago that where we did that for spin chains. So Jan Affleck from field theory had guessed a form for this mass as a specific function of essentially chemical potential dependent velocities and susceptibilities. And then, so for the spin chain could prove it from beta ansatz. And here you can do exactly the same. Okay, so there's just a glorification, so then the effective mass becomes essentially a function of the velocity and the filling as a function of chemical potential and the derivatives of these two objects. Okay, but then if you thought this derivation was, you know, long, then the other one is like something else. But it's still doable. And you could calculate the third order term, the seventh order term if you wanted to. Everything is in there because you have the exact dispersion curve. So in a sense, what you can do from this is calculate effective parameters for a stupidly complicated field theory. You end up writing a field theory that has, you know, ridiculous terms in there, but actually it's exactly solvable. Okay, so there are loads of irrelevant terms that are specified by these things, higher derivatives in x. On the renormalization group, you'd say, oh, you know, these operators have such a high dimension, you know, you take a fourth derivative, you take a 37th derivative, etc. Utterly irrelevant, but actually they're there. Okay? And in here, they all have their coefficients that are specifically fixed so that the system is integrable. Okay, but the field theory itself, so actually this whole thing has really quite a lot to teach you about field theory. What happens to your perturbative expansions when you include these infinite strings of irrelevant terms. That was actually what we were looking at. Okay, but yeah, this becomes more advanced. Okay, and for the spin chains, of course, you can do very similar considerations here. So I don't know if Martin is showing me that, but let's see.
Other questions?
Okay, so a little break and then we